Hello everyone, my name is Sarah Photowat. I'm going to present Amazon Redshift Service History and Architecture as part of my final project for AWS course that I have taken in Johns Hopkins University. In this presentation, I will cover overview of online transaction processing (OLTP), overview of online analytical processing (Olap), and the difference between the two. As part of that, I will go over original OLTP and running analytics reports. Then I will show how OLTP and Olap performance got improved over time, and how the data mart was created. Then I will go over OLTP and Olap architecture, show the differences between data mart and data warehousing, and then I show a generic star schema in a data mart and the star schema that I used it in my demo. Then I will cover AWS Redshift Service Architecture, which includes what is AWS Redshift Service about, why Amazon started Redshift Service. Then I will cover leader node and compute nodes as part of the Redshift architecture. I will explain leader nodes roles and compute nodes roles, slices, types, and pricing. Then I will have a deeper dive and I will cover advanced architectural capabilities of Redshift. Redshift designed to reduce I/O, and it happens through columnar storage, data compression, and zone maps that we will cover each. Also, Redshift data distribution can be a key, all, or even style. We will cover those. And we show how Redshift achieved parallelism. We go over query execution terminologies. We show the stream, segment, and step. And we also show the query execution in parallel through the slices and the query lifecycle. Then I will cover Redshift benefits, and then we look at Redshift Spectrum, a service offered within Redshift, which allow us to query data stored in S3. As part of that, I will cover why do we need AWS Redshift Spectrum and what are our wishes for a new data service, and if Spectrum can cover that. Then we go over Spectrum architecture, feature, and life of a query. In the second video, I have covered Redshift Service Demo. It's a hands-on and it covers following topics. I create Redshift cluster and I configure it. Then I load sample data to S3, and then I load that very data from S3 to Redshift. Then I show how to query Redshift cluster and how to optimize the query. At the end, I create a Redshift snapshot and delete the cluster. Okay, what is online transaction processing, or OLTP? OLTP is characterized by a large number of short online transactions, including insert, update, delete. The main emphasis is put on a very fast query processing and maintaining data integrity in multi-access environment. Effectiveness in OLTP measured by number of transactions per second. Current data is stored versus analytical data. Schema used is the entity model, usually 3NF. It involves queries accessing individual record. For example, update your email in a company database. Typically, OLTP systems are used for order entry, financial transaction, CRM, retail, sales, etc. So in comparison, what is Olap, or online analytical processing? Olap deals with historical data or archival data. Olap is characterized by a relatively low number of transactions. Queries are often very complex and involve aggregations. Olap applications are widely used by data mining techniques. In Olap database, there is aggregated historical data stored in multi-dimensional schemas, usually star schema that we will cover later. And example of it is, what is the profit of your company in last year? Let's look at the differences between Oltp and Olap. Oltp is a day-to-day operation, versus Olap is a long-term informational requirement. Oltp is transactional and clerical data processing task, versus Olap is decision support task for business interests. Oltp is simple and known queries. Olap are ad hoc, complex, interactive queries which access million records. Oltp covers select, update, basically read and write, versus Olap is read-only. Oltp is real-time update versus Olap is a batch update. Data model in Oltp is entity relational versus data model in Olap is multidimensional. Oltp is low I/O processing. Olap is a high I/O processing. Oltp size is 100 megabyte to gigabytes. Olap size is 100 gigabyte to terabytes. Oltp is normalized DBMS. Olap is denormalized. Oltp stores operational data. Olap stores consolidated data. The original Oltp was very slow because users with many daily transactions, including many fast read and writes, would access the same database that the other users running long analytical reports would access. That made it too slow for everyone. The concept of the data warehouse was introduced so that through an ETL process, historic data gets copied to a data warehouse and keep the Oltp database smaller. The benefit was that the marketing and the business side could run their long analytical reports against a separate database. And as a result, both parties would experience better performance. In the previous example, to improve the performance of the business side and marketing side, we went even one step ahead and we separated their databases. This was achieved through two different ETLs. As you see, now the business side can have more sophisticated questions and expect better performance. He can ask, what's my best-selling product? What was the worst performing store? Or marketing can ask, what was my best ad source? What was the best product areas? And vice versa. By now you must have understand that Data Mart is nothing but a subset of the data warehouse. It is specially designed for specific segments like sales, finance, etc. Data warehouses and data marts are mostly built on dimensional data modeling. Let us review the Oltp and Olap high-level architecture. In this section, we have the Oltp. All of our data sources are here, and we have all these transactional users at this level. The data warehouse adopts a three-tier architecture. The bottom tier represents the data warehouse data server, which performs the extract, clean, load, and refresh functions. The middle tier is an Olap server, which is an extended relational database management system which implements the multidimensional data and operation. The top tier represents the front-end client layer. This layer holds the query tools and the reporting tools, analytics, and data mining. What are the differences between data mart and data warehouse? A data warehouse is a large repository of data collected from different organizations or departments within a corporation. Data warehouse is an enterprise-wide organizational level, whereas a data mart is only a subtype of a data warehouse. It's designed to meet the need of a certain user group. In other words, a data mart is designed for a particular line of business such as sales, marketing, or finance. Here is a generic star schema used in data mart and data warehouse. Both of them are mostly built on dimensional data modeling, where fact table relates to multiple dimensional table, and they are related via foreign and primary key. Here is the schema that I used in my demo hands-on Redshift. The fact table here is line order, and dimension tables are part, supplier, customer, and DW date. A customer orders many parts from different supplier, and in every order there are so many line orders. And as you see, these tables are all connected through primary and foreign keys. In this section, I will cover AWS Redshift Service Architecture. What is AWS Redshift Service about? Amazon Redshift is an internet hosting service and data warehousing product. It provides massive parallel processing data warehouse to handle large data sets and database migrations. The sizes are about 160 gigabyte to 2 petabyte online. It also does streaming, backup, restore to S3, and load data from S3, DynamoDB, and EMR, which are the different services in AWS. And also, it provides extensive security features. In general, it's fast, it's cost efficient, it's simple, it's elastic, it's compatible, and secure. Now the question is, why Amazon started Redshift service? Reality is, it's easy to generate data. We can store all data in S3 up to exabyte. Looking at the chart below, it shows that the most generated data is unavailable for analysis. This is called dark data problem, and solving this problem was motivation for Amazon to start the Redshift, and later on Redshift Spectrum. Of course, Redshift is another data warehousing solution. However, the main goal was moving data that were too massive, too slow, and therefore expensive to grow and maintain. And this leads to the concept of big data. Why did we start big data? When your data sets become so large and diverse that you have to start innovating around how to collect, store, process, analyze, and share them. The most important component of Redshift architecture are leader node and compute nodes. As it's shown in the picture, there are one leader node and many compute nodes. Leader node is in charge of communication with outside world and talking to compute nodes. Compute nodes, on the other hand, are in charge of talking to the S3, Amazon DynamoDB, and the rest. Also, it's possible to have one single node where leader and compute nodes are combined. Let us look at leader node roles in more depth. Leader node manages all external and internal communication. It's a SQL endpoint. It stores metadata, and it also coordinates the execution of the query. The parser component of the leader node reads the query and rewrites it. The planner component prepares execution plans. The optimizer component optimizes the execution plans based on the statistic and analytics that gathered. The code generator component generates C++ code. The code distributor distributes the query execution to the compute nodes and assigns slices of data to each. At the end, leader node aggregates the query result received from the compute nodes and passes it to the SQL client and BI tools. Let us review compute nodes' role in more detail. Compute nodes do actual parallel distributed execution of all queries and return the intermediate results to the leader node. They load, backup, restore via AWS S3, they manage Columnar Storage, and they do parallel load from Amazon DynamoDB. Let us review compute nodes and the concept of slices. As it's shown in this diagram, one compute node can have many slices. In this case, it has 4 slices. The disk storage of a compute node is divided into number of slices, as it is shown in here. Slice is like a virtual compute node. Each slice has a portion of the compute node memory and disk assigned to it. It performs query operation that was assigned to them by the leader node. Each slice processes its own data. Slices, once assigned the query portion of a slice, work in parallel to generate query result. Table rows are distributed to slices, and I will show in future slides how this concept works. The number of slices per node depends on the node size of the cluster. For example, each DS1 X large has 2 slices, and each DS1 8X large has 16 slices. We will review the type of the compute nodes in future slides. As of now, we have 2 types of compute nodes, dense storage and dense compute. Dense storage, or DS, allow you to create large data warehousing using hard disk drives HDDs for a low price point. On the other hand, dense compute, or DS, allow you to create high-performance data warehousing using solid-state drives, or SSDs. In this table, I'm showing pricing for different type of compute nodes. As I mentioned, we have 2 types of compute nodes, dense compute and a dense storage. We have different sizes, large and 8x large for each one of them. In this chart, we are showing the number of vCPU, ECU, amount of memory, storage, I/O, and the price. The price for dense computes for large are 25 cents an hour, versus the 8x large is about $4.8 per hour. As we see, dense storage is much more expensive than dense compute. In next section, I will cover AWS Redshift advanced architectural capabilities. In this section, we will review how Redshift is reducing I/O through columnar storage, data compression, and zone maps. We also look at different distribution styles in slices that are key, all, and even. Also, we look at Redshift parallelism aspect, usage of stream, segments, and steps. What does columnar storage mean? Let's look at this sample table. It has 3 columns, AID, location, and date. In a row storage, in a block, we store row by row. Columnar storage means we store data column by column in disk. In this case, in one block we have AIDs, in one block we have location, and in one block we have date. In row storage, for retrieving data, it's required to read the entire row, and this causes too many unnecessary IOs. In columnar storage, each data block holds column field values 3 times more than row-based storage that leads to less number of IOs. An added advantage is that a columnar structure enables much better compression. Another benefit of columnar storage is that when we're retrieving data, for example, we are only retrieving date column, in that case, only the blocks for relevant column gets scanned, which result in less IOs. When we use columnar storage and we apply compression to each column, because columns grow and shrink independent of each other, then we will have effective compression ratio due to having similar type of data that reduces storage requirements and hence reduces IO. If you pay attention to the create table, in this case, we have different compression method for different columns. Let us see how zone maps help reduce IO in Redshift. Zone maps, sometimes also called block metadata, are the information that describes the content of each block, of each column, of each table on the Redshift cluster. These metadata contain per block min and max value. This will prune blocks which cannot contain data for a given query. Therefore, it reduces the IO. Zone maps gets more effective if it's combined by sorting. For example, we would like to find how many entries we have in our table logs for a given date of June 9. In case of an unsorted table and having min and max value for each block, we can find the date with hit and miss in each block. However, if we sort the dates within the blocks, then the zone map is effective, as we will hit the right block in the first attempt. This results in less amount of IO. What does data distribution style mean? It's a table property which dictates how the table's data is distributed throughout the cluster. We have three different types of data distribution style in Redshift. Key means the rows are distributed according to the values in one column. All means a copy of the entire table is distributed to every node. Even means the leader node distributes the row across the slices in round-robin fashion, regardless of the values in any particular column. Data distribution key style means pick a distribution key such as primary key and distribute the data across the cluster nodes. In this example, I have chosen AID column as distribution key, and given the fact the hashing works well, the data is distributed evenly between node 1 and node 2. Now, if there is a large table that gets joined with another large table over the AID, having the distribution key will help drastically. However, choosing the right distribution key is very important. In this example, I have chosen a bad distribution key, which is location. As you see, only two unique values in data exist for the location, San Francisco and John F. Kennedy, and we can only distribute to two slices of the node. Therefore, node 1 is fully populated versus node 2 is not populated. What does distribution style of all mean? It means complete copy of the data will be on the first slice of each node. If the table has less than 1 to 2 million rows, go with the all distribution style. In this example, we have two nodes, and as we see in the first slice, we have the entire table copied in each node. The data distribution of even type means when the leader node distributes the rows across the slices in round-robin fashion, regardless of the values in any particular column. It's usually recommended to use even distribution when key cannot produce an even distribution, and when the size of the tables are larger than 1 to 2 million rows. In this example, we see that distribution style is even, and the rows have been distributed into the slices of each node in a round-robin fashion. In this section, we would like to have a deeper dive and find out how Redshift achieves parallelism. When a query comes from a SQL client or a BI tools, leader node receives it and then it parses it rewrites it and do some planning and optimization, and it generates C++ code and distribute the code among the compute nodes. We have 1 to n number of compute nodes that are divided to many slices. Each slice will do portion of the query, and eventually the result of this query is sent back to the leader nodes. The leader nodes is going to aggregate all these results and send back the result to the client. In order to understand Redshift parallelism, we need to get familiar with query execution terminologies. There is a concept of step, segment, and stream. A plan is made of multiple streams. A stream is made of multiple segments. And a segment is made of multiple steps. So step is an individual operation needed during query execution. Steps need to be combined to allow compute node to perform, for example, a join. Examples of steps can be scan, sort, hash, aggregate, etc. Segment is a combination of several steps that can be done by a single process. Segment is the smallest compilation unit executable by a slice. Segment within a stream run in parallel. A stream is a collection of combined segments which output to the next stream or SQL client. This is a good visualization of a stream, segment, and step. As you see, one stream is made of many segments, and each segment is made of many steps. And we have multiple streams that are happening one after each other. This picture shows that different slices are running different portions of a plan at the same time in parallel. Let's review query lifecycle in more details. When the client has a query through JDBC and ODBC, it reaches to the leader node. The leader node first parse it, then do a query planner and create code. This code gets sent to all the compute nodes. We have compute node 1 to n. They all run pieces of the query and then they return the result back to the leader node. The leader node do the final computation and return the result back to the client. In this section, I will cover Redshift benefits. I have listed some of the Redshift benefits here. It is fast, it is inexpensive, it's continuously managed, security is built in, and Amazon continuously innovate, and it is based on service-oriented architecture. It's fast because there is less I/O, there is a data compression, we have concept of zone maps, direct attached storage. It's inexpensive, number of nodes multiplied by price by hour is not that expensive. There is no charge for the leader node and no upfront cost and pay as you go. It's continuously managed. It has a fault tolerance with disk failure, node failure, and network failure. Security is built in, load encrypted from S3, SSL to secure data in transit. It has an Amazon VPC for network isolation and many, many more things. On Amazon, continuously innovating. As of 2017, the data that I gathered, 140 plus features were added. And it is based on service-oriented architecture. It can communicate with other services that Amazon has, such as AWS EMR, RDS, DynamoDB, mobile analytics, data pipeline, etc. I just posted this slide here to show how many changes have been applied to Redshift since it is launched. It almost releases every 2 weeks, and also it has an automatic patching, which is great. Another major Redshift benefit is the fact that it has huge ecosystem. In the business intelligence, for example, Burst is working with Redshift. In the data integration, Talent D is working with Redshift, and many, many more. Another major benefit of Redshift is it's widely used by Adobe, by UMUC, and many major companies. In this section, I will cover AWS Redshift Spectrum service, which allows querying data stored in S3 without moving data. I was wondering, why do we need yet another service called AWS Redshift Spectrum? We have many choices in AWS for running analytics, data mining, etc., including A, we can use AWS EMR Hadoop and access data in S3. It can scale out to thousands of nodes. Or B, we can use AWS Redshift, which has query optimizer and is as fast as local disk performance. The answer to my question was in one webinar by Amazon. The sentence was, but we have to choose A or B. We should not have to choose, and that was a great answer. What are our wishes for a new data service in Amazon? A service that from one data processing engine can run our queries. However, data can be accessible from all data processing engines. A service that separates database engine from data with an open format. A service that has both great features of scale out from EMR Hadoop and query optimization from Redshift. A service that has throughput of a local disk, and a service that allows scale of S3. With all the above in mind, Redshift Spectrum was created. Here is Redshift Spectrum architecture. The BI application has a query. It's received by Amazon Redshift. It passes to the Redshift Spectrum, and the query goes against the S3 and the result sent back to the Redshift. In this situation, we do not need to copy the entire S3 to Redshift in order to do query on it. Let us review Redshift Spectrum features. It has the ability to use Redshift syntax to run SQL against the S3. It allows you to query data in place using open file formats instead of ETL. It has high concurrency as multiple clusters can access same data. For example, multiple Redshift concurrently can access the same S3 bucket. It's on demand and pay as you go. It's elastic and highly available from any availability zone. It's fast even at the exabyte scale. Let us review Redshift Spectrum life of a query. What you see in this slide is a BI node sending a query to Amazon Redshift leader node. The leader node communicates to a set of compute nodes. However, underneath the cover, we have a Spectrum nodes that are in bunch of private managed VPC. The Spectrum node can access S3 because there is a data catalog that defines dataset stored in S3 or stored in Redshift, etc. The Spectrum, as a result, could query in S3 through an external schema. In step 1, a query has been submitted from the BI tool. In step 2, query is optimized and compiled at the leader node. Determine what gets run locally and what goes to Amazon Redshift Spectrum. In step 3, query plan is sent to all compute nodes. In step 4, compute nodes obtain partition information from data catalog. In this level, compute nodes talk to data catalog and dynamic prune partitioning happening. If your data is partitioned within data catalog by year or date, and if you specify a date filter, AWS Spectrum automatically make it that only those dates in that query scan against. In step 5, each compute node issues multiple requests to the Amazon Redshift Spectrum layer. In step 6, Amazon Redshift Spectrum nodes scan your S3 data. There are various best practices such as storing your data in columnar data, which will speed up these queries. In step 7, Amazon Redshift Spectrum filters, joins, and aggregates. In step 8, final aggregations and joins with local Amazon Redshift tables done in cluster. In step 9, result is sent back to client. In this section, I will cover AWS Redshift Service Demo highlights that I will cover in another video. Here is a highlight of AWS Redshift Service Demo that I have offered in another video. As part of that video, I created Redshift cluster and configured it. I loaded the sample data to S3. I loaded the very same data from S3 to Redshift. I queried the Redshift cluster and did some query optimization. At the end, I created the Redshift snapshot and deleted the cluster. In this slide, I'm providing one way to load data to Redshift. You can split the data into multiple files and then upload files to the S3 and then use the copy command to load from Amazon S3 to Redshift. In summary, I have provided an overview of Oltp and Olap and differences between the two. I provided the differences between Data Mart and Data Warehouse. I reviewed star schema in Data Mart. Also reviewed the Redshift service architecture, including leader node roles and compute node roles. Compute nodes are divided into slices, compute nodes type that are dense storage and dense compute. Also, I went over the pricing. I also covered the fact that Redshift designed to reduce I/O through columnar storage, data compression, and zone maps. I also covered Redshift data distribution styles to be key, all, and even. We went through Redshift Parallelism and Redshift Query Lifecycle. I also covered Redshift Benefits. I also covered AWS Redshift Spectrum Service, which allows querying data stored in S3 without moving the data. And I went through life of a query in Redshift Spectrum. I have provided a second video for Redshift hands-on demo. Here are the list of references that I used. Thank you very much for listening to me, and never stop learning.